Okay, so here's what we were doing last time. We were talking about non-rectangular domains and how do you turn a double integral into an iterated integral when the domain's not a rectangle. Right? And the big idea is to realize, let's see, let me come back up to here, to realize that because of the shape, your inner bounds are going to be functions of the outer variable. Right? That's a big point. And then how do you find what those functions are? Well, again, you recognize that the bound that you're looking for comes from a certain point that you can identify from your picture, which is on some curve that you can identify from your picture, which will have some equation. Then you recognize that, okay, what I'm looking for, that being a value of, well, in this case, it's a value of x, right? And so therefore you solve for x in the equation that you found. All right, so that's our process. We did a couple of examples, and I deliberately made this first example, basically without any algebraic challenges, right? So I wanted to focus on the process, and we did the slicing first, dy dx. And then we did it all over again, dx dy, and that's about where we left off last time. Okay, so that's the process. Now there are some tips and tricks that I think are worth talking about explicitly. So I'm going to start by showing you this example. This is going to end up giving us our first sort of like strategic tip, I guess we'll call it. And so, so our domain is bounded by these two curves. We've got the parabola, and we've got this line. Now, before we go into the double integral question, I do want to talk about the language here a little bit. So it says here, domain is bounded by. This is very particular terminology. This actually means two things. It's commonly misunderstood. This means two things. On the one hand, it means that these curves make up the boundary of the set in question. Okay, right, fine. Cool. Here's the problem. There are actually multiple regions for which these two curves are the boundary. Right? So, for example, you probably weren't thinking of it as describing this area over here, but in fact, that region, it's kind of an infinite region going kind of up and to the right. The boundary is it consists of the blue curve and the green curve. So is that what this language means? Is this D? No, because there is a second requirement. When you say bounded by, it doesn't just mean that we're telling you what the boundary is. It also means that the region is bounded. And bounded means that you can put it in a box, that it doesn't run off to infinity in any direction. So there's various different regions that we could talk about whose boundary consists of these two curves, but there is only one that is actually bounded. So this is the only region we could be talking about. Everybody follow that? Okay. So this is another thing that falls into the category of this is part of your job, right, to interpret the question correctly based on the how it's described. So make sure you're careful about this point. Okay, so there's our region. All righty, now let's see. Let me get rid of that. Okay, so for no particular reason, I'm going to start off by doing x bounds. So we're going to be slicing in the x direction, and this is what our x slices look like. Something like this. And excuse me. Let's see. Let me clean up that mess. So if we want to know what our lower bound is, well, our lower bound is going to come from that point. That point is on these two curves, right? The green curve and the blue curve. It has those two equations. And so given that algebra, I need to solve, wait a minute, what am I doing here? Oh yeah, x. I need to solve for x in that pair of equations because I'm looking for a lower bound that is in fact an x coordinate. Right? Does everybody see how I got to that point? Right. Okay, so we solve for x. Now there's a tricky little bit that happens here. You solve for x, a lot of people are going to get 2. Right? Because let's see, y is x squared, y is 4. That means x squared is 4, so x is the square root of 4, which as everybody knows is 2. And that's wrong. Right? A lot of people misunderstand and talk about the square root. In fact, every positive real number has 2 square roots. Right? And so all we really know from this algebra is that what we're looking for could be either 2 or negative 2. And we're not sure which. So how do we decide? Well, let's look at the picture, and I can just see from the picture here that what I'm looking for is clearly to the left of the origin. That's straight out of the picture, right? I mean, I'm relying on the picture here to draw that conclusion. So because it is to the left of the origin, that means I'm looking for the negative number, and that means that when I solve this for that lower bound, it is negative 2. Everybody happy? Okay, so very similar algebra to get the upper bound. Now let's think about the inside bounds. So remember, per our usual process, we're now going to fix a value of x. We're going to look at that x slice in which we have, well, there's going to be some lower bound for the y integral. And okay, we'll see, what can I say about that lower bound? Well, thank you, picture. By the way, you got to have a picture to draw these conclusions. Right, I'm relying heavily on the picture to see that, okay, well, as I do this y slice, I am going to be starting at that point. So that point, which is on that curve, which has that equation. Wait a minute, what was I doing here? What am I solving for? Well, I'm solving for a y coordinate. So in this equation, I need to solve for y, and y is x squared. Right? Everybody good? Okay. So now, notice every time you go through this process, every time you look for a bound that you associate to a point, which you identify as being on a curve, which you then recognize as an equation, and then you solve. It's always the same process, but the geometry is different in every application of that algorithm, right? Okay. All right. Okay. All right. Now, likewise, the upper bound's 4. Make sure you can do that. I think that's a reasonable analogous to what we just did. Now, here's the thing. I just set up an iterated integral, slicing in that order. Just to see what happens, let's now go in the other order. See how it plays out. Okay, well, starting with y slices. So as I go in the y direction, this is what my y slices look like. And I'm going to say sometimes you just get really lucky. And this first y slice is, I can see from the picture, it's the origin. And what's the y coordinate at the origin? Is 0. Sometimes the fish just jump in the boat, right? And that's really nice. And then likewise, this last y slice, well, it's right on this curve, y equals 4. So when I solve for y, well, I'm going to get 4. So again, sometimes they're freebies that you can just kind of see right from the picture. And in those cases, cool. All right. Okay, now we're going to fix a value of y. Now we're going to think about, as we go in the x direction, and usual process, let's see here, my lower bound comes from that point, which is on this curve, and here's where a lot of students mess up. Very common crash and burn. A lot of students correctly identify that point, that curve, that equation, and then think, okay, I guess it must be x squared that is the lower bound, because they see that in the equation and they just figure, well, there it is, it's looking right at me. The students are not following the process, right? We are not looking for a value of y. Right, look at what we've got here. We are going in the x direction. We're looking for the lower bound for x, and so we need to solve for x in that equation. And when you solve for x, well, you got to do a little bit of algebra there, not a lot, of course, but when you do the appropriate algebra, solve for x, you're going to get plus or minus square root of y. Now, again, you have to look at the picture and let the picture be your guide as to, wait a minute, do I want the plus or do I want the minus? And okay, well, I mean, again, you look here, and I can just see right here in the picture that clearly I'm looking for the negative one, because I'm looking for the lower bound, and picture clearly shows, and so therefore negative square root of y. Everybody happy? Okay, so don't go too fast on this. By the way, a lot of students have had some sort of a multivariable calculus class in high school, and okay, there can be good things there, but a lot of high schools kind of sweep this point under the rug. They studiously avoid any examples where you might have to, worry about getting in trouble when you're playing too fast and loose with this. And so a lot of students don't even know that these landmines are out there, right? So anyway, if you've had that experience, this is how you're going to have to be more careful in general. Okay, yeah.
So as long as you're clever about how you do the balance, the order doesn't matter for which way you do X and Y?
Doesn't matter is a strong term. You are certainly free to slice in any order. You are free to try to slice in any order, but I wouldn't say it doesn't matter. And because you look at these two things, and which one of these would you rather? That's actually the perfect segue into my next point. And so, yeah, which one of these two would we rather deal with? And I'll tell you my personal preference. When I look at this one, and I think, how's my dy integral going to work out? The outside integral. Well, the outside integral, the integrand is going to be whatever this works out to be. Whatever this inside integral is, that's going to be the integrand for my outside integral. And I got to tell you, in this inside integral, I see square roots. And, oh my God, I hate it when there's square roots in my integral, right? So the inside integral, probably fine, no worry. I don't know what f is, so we can't actually see here. But when I get to the outside, I'm doing a dy integral. There's going to probably, seemingly, likely, going to be some square root of y in there. And I'm not optimistic that that's going to be a desirable integral. Right? So, roughly speaking, you just got to keep in mind, whatever are in your inside bounds, that's going to be part of your outside integrand. So try not to put yucky stuff in your inside bounds. Okay, now, so I'm going to say that I like this one better and not so much on that one. So, okay, should we, every time we see an integral, should I write it out both ways and then see which one looks better? And I suppose you could, but that's a fair amount of effort, and I would imagine you probably don't want to every single time, right? What are the odds? So here's my observation of how you can kind of channel yourself in the right direction without actually writing them both down in the first place. And let me address, what was the problem that led to this, right? Why did we get bad news there? And I'm going to say, well, because I had to solve for x. Right? That's what I got when I solved for x. And looking at this given equation, this equation was right there in the statement of the question. And if you have your choice in this equation, would you rather solve for y? Would you rather solve for x? Pretty easy choice, right? I'd much rather solve for y. A, it's already solved for. That's nice. But B, it doesn't have any square roots in it when I solve for y. Does that make sense? Okay. So whatever you would like to solve for. Let's see here. Let me clean up the thing. Okay. Whatever you would like to solve for, put it in the position where that's what you're going to have to solve for. Namely, make that the inside differential. Whichever one you would prefer not to solve for. In this case, all else being equal, I'd prefer not to have to solve for x. Not that I can't do it, but it gets square roots, and I don't want the square roots. Whatever you would prefer not to solve for, put it where you don't have to solve for it. Right? Namely on the outside. Does that make sense to everybody? Okay. All right. Okay. So that's the big lesson, right? Look at the equations that you're given. Think about which one would be easier to solve for, and choose your differential order accordingly. All right, here's another example. You got a triangle here. Right, that's our domain for a double integral. For whatever reason, maybe we're computing mass, maybe we're computing population, maybe whatever, who cares? Some sort of a double integral we're computing. And you can do the slicing in this order. These are your bounds. Make sure you can do that. I'm going to leave those details for you. It's very similar to things we've done previously. But now let's look at what happens when you slice in the other order. What if I do dy dx? Okay, well, so we're going to have our x slicing first. That means we're going to be going in the x direction and making slices like this. And on the one hand, our lower bound for y is going to come from that curve. On the other hand, our upper bound for y is going to come from that curve. And let's think about this curve now. This curve that I have in dark blue here, can I talk about the equation for this curve? Not really. It's two lines. On the left side, it's got one equation. On the right side, it's got a totally different equation. So, bummer, right? So, in order to deal with this, then, I can't just naively say, okay, well, x goes from 0 to 2. Because that puts me in a situation where I can't even find my y bounds, right? My inside y bounds. Because the curve doesn't have an equation. So what we have to do is super annoying, but we have to say, all right, well, we'll start with x going from 0 to 1. The upper bound for y then is just that curve, which has a perfectly nice equation. Play the game, go through, solve for the appropriate, and then that gives you an upper bound that looks like this. But then you've got to say, all right, for the whole second half, as x goes from 1 to 2, I now have a totally different, let's see here, yeah, I do it like that, totally different curve representing the upper bound for y. And again, write down the equation and solve appropriately, etc., and that curve is going to give you that upper bound. Everybody see that? Okay, so again, we've got two different choices of how to do this. I'm going to take this integral that I was asked, and I could do it dx dy, and I get that. Or I could do it dy dx, and I get this. Preferences? Right? Anybody? Being silly, of course. Obviously, we want to do one integral instead of two. Most of the time, I'm sure I could craft some anomalous weirdo example where for peculiar reasons, maybe these are two easy integrals and this is one really hard integral. It's always possible, right? But most of the time, you want to avoid this second case because, again, that's twice as many integrals. Okay, so again, how do we avoid that? And there's different ways you can think about it. Again, you can kind of eyeball and kind of think through the slicing process of the whole thing every time. It's kind of tedious. I like to think of it like this. When I'm doing my outside slicing, as I'm slicing perpendicular to the x-axis, notice at some point I slice through a corner. And because that's, why is there a corner there? Well, there's a corner there because two curves are intersecting, and it's because the two curves are intersecting that it's possible for our upper bound curve to kind of jump from one equation to the other. And so it's because we slice through a corner, arguably, that my x bounds then have the ability to jump over to the other curve. So, nice simple lesson. Try not to slice through corners. Again, there's different ways to phrase this, different ways to think about it. Suit yourself. I find this very satisfying. And it's very effective, right? Thought of in these terms. Whatever order of slicing you're going to do, try not to slice through corners. Now let's look and see if the upper example follows this rule. And keep in mind, we start off with Y slicing. There I am going from 0 to 1. Our Y slices look like this. And I didn't slice through any corners except for the obvious. Obviously, of course, there are corners at the very beginning. No problem. That's where I was starting. Right? I don't have to break off and start a new. I was already starting a new integral, you might say, at those corners, right? And then likewise at the end, at the very end, yes, there's a corner there as well. Again, no problem. I was done anyway, right? So starting and ending slices don't matter. But notice as Y goes from 0 to 1, in between 0 and 1, I don't hit any corners. Everybody happy with that? Okay. So again, that's my preferred take on how to avoid this kind of a problem. Okay. Sometimes you have to find your own domain. So, all right. Here we go. We start off with that surface. That surface, which is a paraboloid, of course. And then this surface, which is some sort of a plane. And then what is the volume that's in between there? Okay, so there's the volume in question. A little bit easier to see over here. We get sort of that other stuff out of the way that we don't really need. That's the volume that's in between. This is what we need to compute. And I can talk about how this is just going to be a double integral. I'm adding up, after all. Let's see here. I'm adding up a bunch of little volumes of little slices like that. Each one of those volumes is a height times the area of the base. Sure. But what's the domain? Right, these little areas, dA, those little areas, dA, here it is, right down here in the shadow, you might say, down in the XY plane. Over what set do those shadows vary? It wasn't given. Right, so this is a scenario that sometimes happens where the domain is something you have to figure out for yourself. It's implicit in the statement of the question, and in this case, let's see, how are we gonna figure that out? Here's the argument I'm gonna make. If you look at that surface right there, what that's telling you is that wherever you might happen to be, this is the formula for z that tells you how far to go up to get to that surface. And if you look at this, now you'd have to do a little work to solve for z there, no big deal. But at a point such as we were just looking at, you can solve for that z, and that tells you how far you got to go up to get to the, to get to the other surface. Okay, fine. So for my z integral, I see the lower bound is going to be this z1, the upper bound is going to be this z2, and here's the big trick then. How are we going to find the domain down here? The domain is going to be the points in the xy plane. I should say the boundary of the domain that we're looking for is going to be the points where this green height is equal to that blue height. Right? And you think as you get closer to the edge, you're going to be kind of moving sort of up the paraboloid, and then you'll be sliding over, and this edge is going to be where this edge is here, and that edge is where these two surfaces intersect, and so you'll have the same z's. That make sense? So what we're interested in as our domain is going to come from looking at the intersection of these two surfaces. Now there's another landmine here, another very common mistake that students make. I've seen it a million times. And basically it's playing too fast and loose with algebra. I don't know where this idea came from, probably high schools if I had to speculate. A lot of people think that there is some notion of setting equations equal to each other. It's really not a thing. That's not a thing, right? But with that in mind, a lot of students, and I'm going to do this in red so we won't, so there's a danger here I want to avoid. A lot of students will do this weird thing where they're like, okay, I guess I'll set this equal to that. That doesn't make any mathematical sense at all, right? For one thing, any one of these equations can be written in several different forms. I could have taken this 7 and subtracted it over there and have stuff minus 7 equals 0. Should I or shouldn't I? And the answer is it's totally arbitrary, and that's part of why this doesn't make any sense at all. Right? So taking one side of one equation and setting it equal to one side of the other equation, that's just not at all how this works. Yes?
Couldn't you set them equal to each other, though, if you converted the one on the right to be z equals something?
Well, yeah. But then very importantly, you're not setting the equations equal to each other. There you are literally saying there are two values of z. There's z1 and z2, and I am literally looking absolutely for the points where these two z's are equal to each other. And that's something that we can see that's motivated by looking at the picture. So, yeah, that's absolutely right. But I think it's important not to call that setting equations equal to each other. Yeah, right. So as she describes, you're going to solve for that z. You're going to solve for that z. And as you can see, I have written down here, oh gosh, okay, setting those z's equal to each other, motivated by the picture, gives me the correct algebra. Everybody happy with that? All right. So now there is some more work to be done here. I'm going to say a quick word about how this algebra works. Again, that is how we identify that curve, namely the boundary of my domain. What is this thing? Well, if you do some standard high school algebra, you can get it down to being the equation of a circle. So this is, in fact, just a circle. It's a circle offset because of the 1 and the 2 that you see there. And the radius is a weird number. This is how this one worked out. Right? But nevertheless, circle. And then that circle, you can go through the usual process and slice it up, and again, always following the usual procedure for finding what the bounds are. Okay, the point is, we had to do the work to find what the domain was in the first place. Okay, now, the one last thing I want to point out about the algebra. About the algebra here. A lot of students have either forgotten how to do complete the square, or their high schools never made them learn how to complete the square, or something like that, right? And that's a problem. A lot of people mistakenly believe that the only algebraic purpose of completing the square is to solve a quadratic equation. And hey, what's the point? We already have a formula for the quadratic equation. I guess we don't need completing the square after all. Absolutely not true. Here you go. Nice little easy example of why sometimes we need to be able to complete the square. So make sure you're proficient with completing the square. If you are not, then I'm sure there are, if you might conceivably still have some of your old high school algebra notes, maybe. Cool. If not, then I'm sure there are internet web pages that would be happy to show you how that works. If none of that works for you, come to my office hours. We'll talk about it. I'll be happy to show you how I've always thought about completing the square. But one way or the other, this is an important algebraic skill that really we should all know, and high schools didn't consult when they decided to de-emphasize that stuff. Okay, 5.3 is a quickie. We're going to cover this entire section in just a few minutes. It's pretty readable, I think. But also, there's really only kind of one trick in it, and it's the idea of what they call changing the order of integration. And ultimately, no big deal. if you have an iterated integral to compute, one thing you can do is reverse engineer what was the original double integral in the first place. In fact, you can find exactly what this domain is for the double integral. Now, normally we don't go that direction. Normally we take double integrals and we turn them into iterated integrals. But if you want to go the other way, just go back to the double integral and then re-slice in the other direction. And that'll turn a dx dy integral into a dy dx integral, and thus changing the order of integration. So that's a big picture strategy. Hope that makes sense to everybody. Details we're going to go through momentarily. Everybody on board? All right, so first let's talk about how to reverse engineer our domain. And I'm going to, if I can get the, okay, that'll be good. Okay, so this is really just a matter of kind of undoing your usual slicing process. When I say y goes from 0 to 1, what that means is I'm going to start at y equals 0, and I'm going to end at y equals 1. So my domain, whatever my domain is, it's going to be somewhere in between those two lines. Okay. Let's see here. What is the lower bound for x? The lower bound for x, I can see it right here. I solved for x and got x equals y. That means the equation for my lower bound curve is x equals y, which is that. And then my upper bound curve, well, I got x equals 1, which is what I got when I solved for x in that equation. X equals 1, which looks like that. Right? So my inside range of values of x here, x goes from the blue curve to the purple curve, and that's for all values of y between these two green curves, and the picture is basically staring at us at this point. Our domain is that right there. Everybody see that process? Just undoing the slicing process. Okay. All right, having recovered our original double integral, slicing in the other order is kind of the usual process. Okay, x is going to go from 0 to 1. And then for any given value of x, y, let's see here, y starts at that point, which is on that curve, which has that equation, so we start with y equals 0, and then let's see, we end at that point, which is on that curve, which has this equation, again solve for y. Y is equal to x. So I've got my new integral with the differentials reversed. Okay. Everybody see how that worked? Okay. Let's see here. What's the point? Like, why would I ever want to do this? What's to be gained? I had what seems at a glance to be a perfectly good iterated integral. Why did I feel the need to go to all that trouble to switch the order of the differentials? And the reason why, in this case, and by the way, this happens sometimes. This isn't the world's most rare thing, but it's not a super common situation. But if I look at how I would have to start this process, I'm going to have to compute the antiderivative of e to the x squared with respect to x. Again, we do integrals inside out. So I'm going to have to find the antiderivative of e to the x squared with respect to x, and sadly, you can't. There is no closed form, no power series. In other words, there is no closed form antiderivative that you can write down. So that's why we felt the need to sort of try something else. This is a dead in the water, can't do it, loser, right? We just can't compute this at all. So, having gone to the trouble that we did, having turned that into a double integral, having turned that double integral into a new iterated integral, fingers crossed, no promises that this is going to make the resulting integral doable, but fingers crossed that maybe it does, and in fact it does. Because when you look at this inside integral here, now you get scared at the very beginning because you see that e to the x squared, and you're thinking, oh my god, I'm in the exact same situation, but no, we're not. This is a dy integral. The outside variable is x. That means x is constant. That means all of that whole thing is constant. And so all I have to do is do the antiderivative with respect to y, plug in these bounds, and you end up with x e to the x squared. So we were able to do the inside integral, and furthermore, the resulting outside integral. Now we're back to x. Right? And again, we have this whole e to the x squared thing, super scary, right? But there's an extra factor of x. And this is an easy substitution. Totally doable. And so this integral actually works out just fine. Everybody happy? Okay. All right. Okay, so that's 5.3. Quick one. Okay, on to 5.4. Y'all will probably be able to anticipate a lot of what we're about to do. We're about to do triple integrals instead of double integrals. Double integrals, as you'll recall, were an extension of the idea of single variable integrals. Namely, we just took the idea of a Riemann sum for single variable integrals and said, okay, well, what would that look like if I were chopping up a two-dimensional region instead of chopping up a one-dimensional interval? And we wrote down an expression. Well, same deal here now in 3 dimensions. So why would we want to chop it up, add it up over a 3-dimensional region? Well, maybe you're looking for mass in a solid, or maybe you're looking for probability of a certain event with a PDF, whatever. Maybe this is a fish tank that has algae growing. I don't know does algae grow in the water, or does it have to be on the whatever? Maybe you got something floating in your tank and with a non-constant density, and you want to know the total quantity of whatever that floating stuff is in your tank. So, as is the case with every other kind of integral that we've seen, we have a new kind of a domain. We want to be able to chop it up into pieces and then add over all those pieces. It's just that now it's a 3-dimensional domain instead of a 2-dimensional domain. All right, well, what do those little pieces look like? The little pieces look like this. They're not sub-intervals. They're not sub-rectangles. They're now sub-boxes, maybe, I think would be a reasonable thing to call them, right? Sub-boxes. I can talk about when I slice up the interval from E to F on the z-axis. I can talk about what those slices look like. We've already talked about how to slice up on the y-axis and how to slice on the x-axis. That we did all of that stuff with double integrals. That's all exactly the same. So this is really very, very similar. And as such, we define, I'll say we write down this expression here. This is our 3-index Riemann sum. This is how you chop up, add up on a solid. Notice that on each piece of our 3-dimensional domain, there's something times volume. What would I want to multiply by volume? Well, stuff per unit volume. Right? Volume density. If you have any accumulating quantity, and if you know how much of that quantity per unit volume there is, you can multiply by these little pieces of volume, get the correct answer on each individual little piece, and then add up over all the pieces. It's just like with a double integral, except three-dimensional instead of two. Volumes instead of areas. Three indices instead of two indices. Everybody buying that? Many examples to follow, of course. Okay, so this is a promising computational strategy. So name and notation. The name is triple integral. The notation is this right here. Again, I think this notation makes a lot of sense. I call all of this, or I shorthand all of this with dV because that's what this represents a little piece of volume. That was the whole point of delta x, delta y, delta z. That's that little piece of volume right there. Right. Again, I'm making up a new symbol. I'm making up this symbol right here. This is what I'll call the triple integral symbol. That represents adding up over three indices, as you see we have here, because we're going to have to add in the x direction and in the y direction and in the z direction to get all of the little sub boxes in this whole, larger box. So, okay. And last little point of emphasis, again, think of this as a single symbol, right? This is, I have not yet discussed iterated triple integrals. This is not, as I have it written here, this is not a single variable integral of a single variable integral of a single variable integral. It's not what it is, right? So this is a single symbol. That is the triple integral symbol. It is motivated by what you can probably guess is going to happen. Yeah, we are going to relate this to triple iterated integrals, but for the moment, that's not what that is. Okay, examples to follow, but does anyone have any questions so far? Everybody buying it? All right. Same disclaimers I gave before. Y'all don't need to worry about irregular partitions and test points. The case is we're going to consider the integrand's continuous. None of that makes any difference. Certainly not computationally, so not our problem. Okay. But again, beautiful math. Okay, let's see here. So moving along, suppose I have a rectangular region and I want to know what is the mass, the total amount of mass that's in that region, where the density, the mass per unit volume at any point in the domain is given by some function of x, y, and z. So this is now mass per unit volume instead of mass per unit area. Right? How am I going to add up all the little pieces of mass? All right, well, the first observation, mass is an accumulating quantity. The whole is the sum of the parts. Chop it up, add it up. Is that cool? Everybody happy with that? Yeah. Okay, on any given little piece of mass, how much mass is there in one of these pieces? Well, it's mass per unit volume times volume. Right? It's just like when we were looking at double integrals, we talked about mass per unit area times area. This is just the same idea. It's doing with mass per unit volume what mass per unit volume was intended to do. Namely, you multiply by volumes to get mass. Okay. And you see I end up with a triple integral. Okay. Notice as well I'm using the kind of the integral shorthand. I didn't use Riemann sum notation here. This is a Riemann sum. Right? There's no M axis. Right? This is shorthand for a summation. And likewise, this is a Riemann sum too. I think it's really important to remember and to remind yourself constantly. This is a summation, a limit of a summation, and this notation is just for notational convenience. Right? This is representing Riemann sums. All right. Okay, is everybody happy with that first example? So I have a conceptual warning to give you. this is just the tough reality that we're going to have to deal with. Let me remind you of some of the ideas as they've developed. Y'all learned single variable integrals long ago, and you learned probably, almost everybody does, that you thought of integrals as representing area under a graph. And this is, kind of the most common way to think about single variable integrals in a single variable calculus class. But I've been pushing this other point of view, right? Graphs are not always what we're looking at. In fact, they are usually not what we're looking at. So having your intuition for integrals centered around something that's rare, right? I think it's a bad idea. I don't think it's a good plan at all. I suppose it's a nice little visual crutch in certain circumstances. Okay, I guess. But really, most of the time when you're doing an integral, we're not interested in area. Most of the time, you're interested in some sort of physical stuff, right? And again, y'all are mostly engineers. Y'all are interested in stuff, right? So, all right, well, for example, if you have mass distributed across an interval, this is literally just adding up all the little pieces of mass. So I would encourage you to think about this. Have this picture in your mind instead of that picture, because this is, again, what you're going to see most of the time in practical applications. Okay, likewise with double integrals. Again, we started with this point of view here just to kind of get the ball rolling. And but then, I pointed out that most of the time when you write down a double integral, it's because there's a two-dimensional domain and you're interested in stuff associated with that two-dimensional domain. Maybe it's mass. Maybe it's population. Maybe you're counting the number of people in this weird-shaped little country or whatever. Right? Maybe this is a pond in your backyard and you want to estimate the number of fish. I don't know. Whatever. Right? Okay. So, again, I recommend this point of view because of its likely relevance to what you're going to actually see. But here's a second reason, right? The second reason is what we are now encountering. Now that we have triple integrals, if you wanted to extend this picture here, this picture here, now for triple integrals, well, wait a second, a one-dimensional integral, you had a two-dimensional picture. A two-dimensional integral, you had here a three-dimensional picture. So for a three-dimensional integral, well, guess what? If you wanted to make sense out of extending this analogy, you would have to draw a four-dimensional picture. Losing. Can't do it. Right? So this is my second reason that I get the creeps when I think about this point of view of thinking about integrals. It's unsustainable. Right? So, whereas on the other hand, no problem from this point of view over here. One-dimensional integral, one-dimensional picture. Two-dimensional integral, two-dimensional picture. Three-dimensional integral, three-dimensional picture. No problem. All good. Everybody see the issue here? Okay, so here's a common, again, point of confusion. Just seen this a million times. A lot of students are like, you know what? I've been doing this for too long. This is how I'm going to, just for convenience, I want to keep thinking of single variable integrals this way. And then they want to think about double integrals this way. And then for lack of options, they recognize they have to think about triple integrals this way. And then they get confused because they have a three-dimensional picture here and a three-dimensional picture here. And they're like, wait a minute, how come sometimes when you have a three-dimensional, it's a double integral, and sometimes when it's three-dimensional, it's a triple integral? And well, because they're apples and oranges, right? And again, they don't have a consistent point of view how to think about these things. So it's not that you can't, but this is going to be confusing, right? So and I'm out of time anyway, so let me just make my last bid. I strongly urge that you persuade yourself toward this point of view of single variable integrals, this point of view of double integrals, so that you can have a consistent analogy, fair comparisons, apples to apples, to help you understand triple integrals. Y'all have a good break. See you later. See you on Wednesday. Don't forget about attendance.